Let's take a look at orthogonal sets. What is an orthogonal set? Well, it's simply a set of vectors where each pair of distinct vectors is orthogonal. Now, if you'll recall from our last video, we said if the inner product of two vectors is equal to 0, then they were orthogonal. And so that's what we're going to do is we just have to check each pair of vectors. So in this case, for my example, I will take the inner product of v1 and v2, and that gives me 4 times -1, so -4, plus 3 times 0, plus 2 times 2, and that gives me 0. So because that's 0, so far so good. Then I'll check, say, v2, v3. And again, I'm just checking the exact same thing. So I'm saying 0 plus 0 plus 6. Well, obviously 0 plus 0 plus 6 is equal to 6, and therefore it's not equal to 0. So I can continue checking. Obviously I can take v1 inner product with v3, and that would give me 0 plus -6 plus 6, which is 0. But it really doesn't matter, because once you have found that you have a pair that is not orthogonal, that means the entire set is not orthogonal. So in this case, for my example, I would say that this set of vectors is not orthogonal. Let's take a look at another example together, and we're going to get to that stuff in green in just a moment. So let's focus on the top of the slide. Let's show that the set of vectors v1, v2, v3 is an orthogonal set. So just as we did last time, I'm simply going to find the inner product of v1, v2, the inner product of v1, v3, and the inner product of v2, v3, and if they are all 0, then I have shown it's an orthogonal set. So v1, v2 would be 2 times 1, plus 1 times -1, plus 1 times -1, which is 0. v1, v3 would be 2 times 0, plus 1 times 4, plus 1 times -4, which is 0. And then v2, v3 would be 0, plus -1 times 4, plus -1 times -4, which is 0. So I've shown that it is an orthogonal set. My next theorem tells me that if I have a set of vectors that is an orthogonal set, as I do here, which I have just shown, that are of course non-zero, then S is linearly independent, so those three vectors are linearly independent, and hence a basis for the subspace spanned by S. So if they ask us to find a basis, we're just basically dealing with, is that set of vectors orthogonal, and that's going to tell us. So this brings us to our next theorem. What this theorem tells us is that if we have an orthogonal basis for a subspace W, then for each y, which y is just some vector, so for each y in our subspace, the weights in the linear combination y equals c1 u1 plus c2 u2, etc. are given by this formula. So that might look a little bit complicated, but it's going to make much more sense once we do an example. But here's essentially what it's saying. We have dealt with this before, a linear combination. We know how to solve for weights in a linear combination. We do row operations, and we're able to find those weights. So essentially what this is saying is if you have an orthogonal basis, instead of having to do all of those row operations, you get to use this handy-dandy formula. So let's take a look at how the formula works. So let's take a look at a practice using that, because it will not make sense really until we actually do one. So here we have a question that says the set S is an orthogonal basis for R3, where they've given me the three vectors u1, u2, u3. They want me to express y as a linear combination of vectors. Now I want to point out that up to this point, if we weren't dealing with orthogonal basis, and I just gave you a similar question, the way that we would go about solving this is you would say this is 1, 2, 1, 1, -1, 1, -2, 0, 2, and augment that with 1, 2, 6. and you would do all of your fancy row operations, and when you did, you would get 1, 0, 0, 11 sixths, 0, 1, 0, 5 thirds, 0, 0, 1, 5 fourths, and then if I asked you the same question to express y as a linear combination of vectors, then I would say that y is equal to 11 sixths times u1 plus 5 thirds times u2 plus 5 fourths times u3. I don't know why my vectors kept getting bigger, but you get the idea. Okay, so up to this point, that's what we would have done, and that's what we would continue to do if we weren't dealing with an orthogonal basis. So we're dealing with this theorem that says, hey, bonus, if you have an orthogonal basis, let's instead use this formula that says we can find these weights that we would find using all of the row operations, which obviously I didn't show. We can instead use this formula that says the weights can be found by taking the inner product of y times whatever your vector is over the inner product of that vector with itself. I's, those are all i's, you get the idea, or j's. I guess I should keep them all the same. So let's take a look at what we're talking about here. I'm looking for, and again, I already know the answers are 11 sixths, 5 thirds, and 5 fourths, but let's go ahead and compute them now using our handy new formula. So if I want to find C1, it's telling me to take the product, the inner product of y times u1, so y dot u1, u1 dot u1, which would be 1 times 1 plus 2 times 2 plus 6 times 1 over, and then u1 with itself, so 1 times 1 plus 2 times 2 plus 1 times 1, and 1 plus 4 plus 6 is 11, and 1 plus 4 plus 1 is 6, which matches 11 sixths. So now let's do C2. C2 would be y times u2, u dot 2, and then u2 dot u2. So y times u2 would be 1 times 1 plus negative 1 times 2 plus 1 times 6, and u2 by u2 would be 1 plus negative, 1 plus 1 plus 1. And that gives me 5 over 3, which matches. And then let's do one more, which is C3, which is y times y times u3, and then u3 dot u3. And that gives me 1 times negative 2 plus 2 times 0 plus 2 times 6, and then u3 dot u3 would be 4 plus 0 plus 4, and that gives me 10 over 8, which reduces to 5 over 4. And so that's exactly what it's telling us, is instead of doing all of those row operations, you can use this formula to find those weights. And again, how would I then write my solution? Y is just a linear combination of vectors, and so it's, remember, C1 U1 plus C2 U2 plus C3 U3, and I've just used my formula to calculate C1, C2, C3. So Y is equal to 11 sixths U1 plus 5 thirds U2 plus 5 fourths, once I reduce it, U3, or again, write it like this with those vectors written out. Here's a practice for you to try on your own. So you are given that this is an orthogonal basis for R3. You have the three vectors. I want you to write y as a linear combination of those vectors. So press pause, try this question. When you're ready, press play to see how you did. Again, all I'm going to do is use that formula that says to find the scalar or to find the weight, I'm just going to take y times whatever my vector is, so we'll just say Vj, and then the dot product or inner product of Vj with itself. So that's what I'm going to do then. For C1, I'm going to take y times v1, and I'm not going to write that out this time. So y times v1 would be 0 times 13, or 0, plus 2 times 3, which is 6, plus 4 times 1, which is 4, which gives me 10. And the denominator of my fraction would be the dot product of v1 with itself. So 0 plus 0, 0 times 0, 2 times 2, and 4 times 4, which gives me 10/20ths, or 1/2. C2 would be y times v2, so 13 times 5, negative 2 times 3, and 1 times 1. And the denominator would be C2 with itself, so 25 plus 4 plus 1. So that gives me 60 over 30, which is 2. And then for my last one, C3, I've got y1 times v3, so negative 39 plus negative 18 plus 3 over v3 with itself, so 9 plus 36 plus 9. And that gives me negative 54 over 54, which is, of course, just negative 1. Which means if I'm to write y as a linear combination of vectors, then y is equal to 1/2 v1 plus 2 v2 minus v3. Or, again, more preferable, actually using the vectors, 1/2 0, 2, 4 plus 2, lost my place for a second, 2, 5, negative 2, 1, minus negative 3, negative 6, 3. That's all we got to do.